Hello, this is Alex Yazdani. I'm doing a video demo for Lab 2 of EE533 in the spring of 2025 with Professor Young Cho. So in this lab, we had to implement a few modules and schematics and then also do it in Verilog. So the first part was to implement an 8-bit synchronous adder. So to do that, I just built a full adder and I just used the XOR gate 3 input for the sum outputs and then a majority function for cout, fairly straightforward. And then to make that into an 8-bit adder, we just instantiate it 4 times and chain the carries like so. And then to make it synchronous, we just register the inputs and outputs. So we actually don't want to use this module when we scale this up to a 32-bit adder, and that's because we don't want the carries to be registered, because then we would need 4 cycles to calculate this sum. So the next part of the lab, we needed to create a 32-bit ALU, and that needed to have a couple functions, the adder, a subtractor, a shifter, and then 2 others which I implemented an AND and an XOR. So first, to look at the 32-bit adder, I just instantiated the 8-bit adder 4 times and connected the carries, and then did some bus taps for the inputs, and that's all fine. For the subtractor, it's the same thing, except we invert the B inputs and then we force the C in to be high. That takes the 2's complement so that we can just use an adder to subtract. For the shifter, the specs were not very strict, but I did a logical shift left 1 bit, and then you just shift in whatever the least significant bit of B is. So here there's just some bus taps and some buffers. For AND, it's just 32 AND gates. I just instantiated this 32 times, and same with XOR. It's just a bitwise XOR, so very simple. But then if we look at the top module, we just instantiated each one of these operation modules, registered all of the inputs, and then registered the output, and just muxed all of the outputs from each operation. Also, there needed to be some buffers, and this just has to do with we instantiated the mux 32 times, 1 for each bit of the result. And then the opcode is 3 bits, so each one of these bits needs to go to one of these select inputs, and a buffer was needed to basically connect them. Because of the ISE tool, it seems to require that. So in total, we have 3 signals that are 32 bits, and then 3 bits of opcode. So that's 99 total flip-flops here. And then there's an additional 2 signals for clock and reset. So the I/O in total is 101, and the number of flip-flops should be 99. And then we had to repeat this entire thing in Verilog. So on the top level basically just takes the combinational ALU and then just registers the I/O. 1 level beneath that, it's instantiating each of the operations and then muxing the output. That's what this case statement is. And then, then there's all the code for the adders, the subtractor, the shifter. It's just a shift left, AND gates. So I tried to implement everything very similar to how I did it in schematics, but of course it's not exactly the same. So actually, when I looked at the synthesis files, it seems that the Verilog implementation has more slices. Doing things in schematic is generally more efficient, better utilization than if you do things in Verilog, especially if you're coding behaviorally. I tried to code structurally, but looks like there were still some things that I didn't do completely optimized. Otherwise, the implementation would have been exactly the same. So just to do a quick simulation here. This is of the Verilog module, and I'm just going to do this one simulation, but in my report I have very detailed information on all of the modules and submodules and how I simulated them, so please refer to that. for extra verification that I completed the lab. But here, this isn't exactly testing each of the operations in all of their corners. It's definitely not exhaustive. This is mostly just testing that the top level works. So since the I/O is all registered, the outputs actually arrive a cycle later than the inputs. So here, when the opcode is 0, that's addition. So the inputs are 5 and 3. So then a cycle later, we see that the result comes to 8. The next one would be subtraction. So when the opcode is 1, 5 minus 3 is 2. So we see that at the output right here. Then the next one is a shift left, then and an XOR. And then the last 3 opcodes, 5 through 7, should just force 0. That wasn't a spec, but I had both my schematic and my Verilog file do that. And yeah, that's about it.